So I will introduce the next speaker, Mr. André Hürkamp from the University of Braunschweig. He's head of hybrid lightweight structures. And now I welcome you, André, and I think you have got an interesting presentation about virtual prototyping for us.
Yeah, thank you, Stefan. I'm glad that I can present here today about an integrated computational approach for manufacturing of lightweight structures. Is there any trick how I can use it? Oh, like this one? Okay, but maybe I will start with something that is not... Actually, there should be a video going on. Anyhow, so maybe now it's maybe less impressive, but I wanted to show you a material which is maybe not lightweight material as you think of it at the moment, but just as a little teaser, we can also build with additive manufacturing of concrete three-dimensional lightweight structures. For example, we are able to build up these columns and then reduce weight and material by introducing such kind of reinforcing ribs which are additively applied on this ball. And here it's quite coming from nature that the process itself, it's additive manufacturing, that this process then defines mainly the properties of the structure. But maybe with this little not so typical material for lightweight, I will go into my agenda today. So I will talk a little bit about an integrated computation product and production engineering. So it's what the speaker before also said, it's always the process defines its properties. Then I will show you two use cases, one from thermoplastic composites and one additive manufacturing construction, and I will end up with a conclusion and outlook. So if we see this chart, it's basically in the center we have our process parameters, and we use standard finite element simulation or different methods in order to identify process impacts. So first of all, we want to know our process boundaries, but then we want to know what are our structural parameters and how do they affect the product properties in the end. So for example, if we have fiber reinforced composites and they are formed or molded somehow, the fiber orientation is very decisive for the final strength of the body. And this can be done by virtual process chains, introducing finite element simulations and so on. This is quite standard approach. You simulate the process, you map your results to your structural analysis, and then you get your product properties you are interested in. But if you look on the right side, so we have the process and the product, but there's always the process chain and the corresponding factory where these process chains are located. And if we have deviations on the single process that influence our product, it will also influence our process sequence, our number of machines we need, lot times, and so on. So also this has to be considered. So it's not only the product itself, it's also the production for the product, the factory, what kind of technical building services do I need. And the challenge here is that we have different simulation paradigms. So the process simulation, the structural analysis of a product, this is very high fidelity, finite element, physically detailed models. But on a factory level, we don't care about the temperature distribution at in the component, for example. We only need to know how much energy do we need, how much time do we need. And this is a very large optimization, because if we go for sustainable, less energy use, for example, then during production we have to look at the right side, but we also always have to play it back to the process and to the product. How does it influence my product, and what is maybe my product properties I need, and what is maybe the best way to produce them. To show you this procedure in a little bit more detailed example, I will talk about overmolded thermoplastic composites. These are a combination of continuous fiber reinforced thermoplastic laminates or woven structures like organosheets, and then combined with an injection overmolding of a thermoplastic polymer, which is usually of the same nature as the matrix of the organosheet. The process is that after heating, this can be done by infrared heating or by an external furnace. It's transferred into the mold. Then when the mold is closed, the thermoforming, so forming process for the thermoplastic laminate occurs, and then we have the overmolding by the injection molding machine, and then we have demolded. And everything can happen on a single injection molding machine, which makes it quite efficient because we have a high specific stiffness and strength due to the continuous fiber reinforcement, and we can also integrate a higher degree of functional integration due to the injection molding. But what is very decisive here for our structural integrity at the end is the bond strength between the two components, the organosheet and the injected mold. And this bond strength is mainly, not only, but mainly influenced by the temperature history during the process. And this is what we would like to analyze. And then actually there should be another video of the process, but you can visit our booth at stand B16. I will be there also today, and I can also show the video of the production process, how it is done. So, but we now want to focus, in the first stage, we want to focus on the bond strength, because this is decisive. Of course, there's fiber orientation, there's a shrinkage and so on, many parameters that can influence our structural properties, but here we look especially on the bond strength. And as you can see here on this example, this is a very academic example where we produce some testing specimens, some ribs, and what you can see here is the contact time displayed, which is the time the interface is heated above melting temperature. And of course, the thermoplastic has to be melted, otherwise we don't achieve any bonding. And what we can see here is, first of all, that the distribution is not constant along the flow path, so it's varying along the flow path, which means that in the end we will get different properties at different locations of the structure. And as you can see, and it's quite obvious, it is the contact time is very depending on the temperature and on the initial temperature of the organosheet, for example. So if we go in with 120 degrees, we have actually no contact time, very low contact times. And if we increase the temperature, then we have quite high contact times. And usually this white thing should also disappear. Then we can see, I hope you can still see it. It's a contact time here, and we can see that if we do experimental tests on the bond strengths, on the left side you have the bond strengths, you can see the lesser the contact time, or the higher the contact time, the higher the bond strengths will be. So we can define some quality areas where we have excellent, good, or poor bond strengths. You can also see from the scatter that this is not the only factor, but there's a clear trend of the interface temperature. And how does the interface temperature look like during the process? So if we look at the whole process chain, we have some heating. Then the interface or the organosheet is heated over melting temperature, and usually a lot more over melting temperature. And then it's transferred to the mold where the thermoforming starts. And since this mold is usually cooled, so 80 or even 30 degrees, depending on the polymer we use, then we have already a decrease in temperature at the interface. And we have to ensure that we still have a lot of temperature inside the material when we start with the injection molding to get a good bond strength. But of course, during demolding and during all the process, some failures can occur. So then we have to wait at some minutes, and then we have maybe a decrease, which can be critical. So we have to analyze how big is the influence of temperature on our body, on our structure. And yeah, therefore, I think I can skip this because it's not so much to see. It's also an animation. There is the thermoforming. process. So first of all, we have to simulate the forming. And what you can see here is that due to the cavity and the sliding above the die of the mold, we have an inhomogeneous temperature distribution due to the local contact with the die and with the mold. So we have to map this information, and we know for the injection molding. And as you can see, we have in the center where the cavities are, we have very high temperatures, which is good because there's where the actual bonding occurs. But also on the sides, we can see that due to the movement of the organosheet, we have some temperature decrease, which is maybe leading to a poor bond strength. And then in the process chain, the second step is then the injection molding, where we use, in our case, we use Autodesk mold flow. We can simulate the flow problem, the mold flow. And what we can achieve then is the temperature, the pressure, and all necessary data for the bond strength at the interface over time, because it's a time series. It's not enough to be 1 millisecond above melting temperature. It has to be over a long time, and we also need a certain pressure to get a good bond. Therefore, we developed a model which is implemented in a post-processing routine in MATLAB, and there we can compute the bond strengths with respect to the time series of these values. And as you can see here, for example, this is the bond strength. It's varying between 0 and 18 megapascal here in this example, and we can see that it's locally not homogeneous. So along one rib, we see that on the outside it's quite low because there we have a high influence of the cooling, and in the center where we have the cavities and we have hot air, let's say, during the process, there we have a very good bond strength. Okay, I will try to speed up. So, but as you can imagine, these simulations are all very time consuming, and in that case, running one set of parameters means set up a forming simulations, map the data, set up injection molding simulation, takes a lot of time, modeling time, setting up the simulation, and also computation time. And if we think from the product to the whole factory, then we have a multi-scale approach which is not easily, cannot be done that we adopt every time, every parameters, wait 1 or 2 days until we get the results. So therefore, what we do in our research is to develop some surrogate models that speed up the simulation. So we have all the physics from the FEM. We do parametric studies. And we solve this kind of high fidelity problem. But this is done anyway. So during the engineering process, this is done many times. But you can use those data because you can use machine learning, you can use other model reduction techniques, and you can already extract the information of the process, of the physics from this high fidelity problem and store it in a database or whatever, and you can make a surrogate model out of it which contains more or less all the physics, but is very fast. So we talk here about a prediction of a physical reliable bond strength within seconds or milliseconds depending on the device. So, for example, you can also run it parallel to the process to act as a quality gate, for example. And here, if we look at a surrogate modeling, we have a parametric analysis with 100 samples, so it's actually not so many simulations. We use the principal component analysis to reduce a little bit the number of degrees of freedom, and then we get a very good prediction. If you see the result from the CAE simulation and the surrogate prediction, it looks almost similar. And if you look at the relative error, we have areas where we have a very high relative error, but in average it's quite low. And here on the right side, you see the comparison between experiments in gray, our bond strength model in green, and 2 different approaches of the surrogate model, and we can see that all are maybe not perfect to the experiment, but our bond strength model and our surrogate models are very much on the same level, so it gives us a very good and very fast prediction. So I'm running a little bit out of time, but what is now interesting is that with the surrogates, we can improve the process, but we can also improve the process chain and the whole manufacturing system. And we can, since it's so fast and online and can run online, we can also go into operation. So either as a virtual quality gate, or we can really go on the process chain level and do a data-based or simulation-based, data-based adaptive process chain control. And then you can play different scenarios. Since we know that the temperature is very decisive in this process, we have different production zone temperatures tested with a variation and different failure probabilities, and we could see that our quality rate can increase drastically if we consider, for example, the production zone temperature. By this case, you can also then see that maybe you would use here the dashed line and say that if the initial temperature of the organosheet and the transfer time is too long, so the time is sorted out and there will be no good bond strength. But actually, if we are in a hotter environment, even more parts could be still good, and we can increase the quality rate in this case and make the process chain operation. How much time do I have? I would like to come back then, because since this conference is not only for automotive or for classical composites, it combines all kinds of industries. This approach I showed you is a computational approach. That's a good thing about it. It applies also to additive manufacturing construction, where we have a collaborative research center at the TU Braunschweig together with TU Munich. And there, as I said already, it's quite the same, that the process itself defines my final structure. We apply this now for concrete, but of course this approach is so generic, you just exchange the material model and you can simulate the time-dependent properties. It's directly coupled with the printing path, so there is no cut geometry used, so you can really simulate what you print. And here we use an integrated approach that is then able to optimize the multi-model-based printing, and also can act as a surrogate if we apply this method then to those things. So we get printing data like geometric information, printing speed and nozzle distance, and maybe additional informations we can get from the machine. And from the preprint data, we have our cut model, our geometry, robot model, and then we can exchange the material model and we can optimize online, or at least in advance, our process. So with that, I would like to conclude. I think I can skip this slide maybe and come to the questions. And thank you very much for your attention, and I'm open for questions.
Yeah, Andre, thanks a lot for your presentation.
Yeah.
Do we have any questions in the audience? Again, we have got the microphones left and right. Please use it, so it's easier for everyone to understand it.
The machine learning thing, you tested this with several, let's say, simulations of the same part, or did you use several parts to have a more holistic model?
In this specific example, we used the same part. But yeah, like this is the question, how general can it be? Usually if you have in your company, for example, you have different part geometries, you can store them in the database and maybe you can learn from that. But actually the transfer from one geometry to another, that's the difficult thing. And where we are looking now, what can be a possible solution.
Okay. Any other question? So I have one, and it's about the virtual prototyping from the design to assembly line, more or less. That's the objective here, from the product to the factory, you told. Finally, if I want to think about the sustainable or more sustainable materials, how big would be the effort to change here the materials and to see the effect on my whole chain? Do you have any assumption for that?
You mean instead of polymers, I can use bio-based material, for example? Yeah, of course, you have to know the material properties, and for, let's say, bio-based materials, this is not so easy and not so deterministic, maybe. but then the framework itself is generic, so you can exchange the process, you can exchange the material data, but if you want to really be fast, I mean, this can take days or months during the development if you go the whole process chain. But if you want to be fast, you have to know your process boundaries, and then you can set up a parametric study. This will maybe run for a week or two, depends on your problem size and your computational power you have. But then this whole optimization in the end can run in seconds or milliseconds. But it's the matter of time you spend before you have this valid surrogate.
Okay, that's important to know.
Yeah. Usually you run those simulations in the company, for example, and you run it several times, and then only the best one is chosen in the end, but you can learn so much from the others, and if you store this and have some intelligent machine learning methods or something in that area, then you can learn a lot from the history already, that you can not start from the beginning for the next part.
Thanks a lot.